let's continue talking about SUMA and the data that we've been looking at. So this, if you've been following the series of videos, we just finished our first kind of tour through using the SUMA GUI interactively, and we ran this command to go to this directory and these to look at the data. Again, the SUMA keystrokes cheat sheet is open and available. And then there are also a lot of the functionality that we looked at here. So the button presses, recording, all this kind of stuff is here. All right, so let's keep talking about what we're looking at here. This is just a little bit more about the technical layers of AFNI and SUMA. And as we noted, the way that they communicate or talk and send information back and forth from the GUIs is through network sockets. And so we'll take a look at another video how you can control this, but the easiest way to do it is to just have one AFNI and one SUMA, and then you hit open at a time, and then you hit the T key and they'll talk to each other. If you need to have multiple AFNIs and SUMAs open and you want certain of them talking, basically you can specify the port that they're talking on, and it's kind of like having shortwave radio where if you know the frequency you can connect and things like that. So we'll take a look at that in another video. In general, I typically have one AFNI and SUMA open anyways when I'm making images or analyzing data and that, so that's not that big a restriction. We looked a little bit at about what a surface is made of, and again, we just have to remember when we look at this that it's not actually this kind of continuous, smooth thing, but it is a mathematical object that is discrete. It's made up of nodes, and then those are edges connecting various nodes. And we have to make sure that there aren't bad properties of the surface, like it crossing back on itself, and things like that too. It's called a topological defect. A really important thing to separate here is sometimes we use the term geometry or topology a little bit untechnically and kind of confuse the thing. So let's be quite clear. The surface geometry refers to where the coordinates of the nodes are in space, x, y, z. So basically, in some sense, every node, it's a little bit independent of the other ones. It's geometry in that, but the geometry of the surface is basically the XYZ of where the nodes are in space. Fine. The topology relates to the fact that the nodes are connected, and so the edges matter here, and the topology is basically the way the edges connect the nodes, the connectivity in a sense, in a different sense than how we often use it in MRI and things like that. Okay, so what is the consequence of having this, and why do we care about these? Well, what we've already seen usefully already is that surfaces can have different geometry but the same topology, and actually that's what we've used already when we look at these families of surfaces here. If I can demonstrate in the terminal, so if I run this SUMA 00 script again quickly, that if you think about here, now if I hit the period key or the full stop, okay, now I have a different surface. I hit the comma and I'm just going back. These are two surfaces, in this case these are two separate surfaces that have nodal correspondence, but this surface and this surface are the same, it's just I inflated one. I changed the position of all the nodes, but I didn't break any of the edge connections. It's like inflating a balloon, right? If you draw a circle on a balloon and then inflate it, you've changed the geometry of the balloon because every point on the surface occupies a different XYZ location. You inflated it, you pushed them around in space. However, the way that they were connected, the topology of the balloon is still the same as it was before it was inflated, assuming you didn't pop it. If you pop it, okay, now you're going to change both the geometry and the topology. But if you inflate something here, this still has the same topology. And as we see, if you've already seen the drawing on the surface video, the benefit of having this topology is it's easier to draw on here. Certainly visually, it's easy to see the entire surface more than here because I don't lose things in sulcal and gyral features. And again, I'm not changing the data. I'm not kind of breaking the data in any way. I'm just changing its geometry, because with surfaces, it's really the topology that's important, and we can basically play with the geometry for something that's convenient. Okay, so there, that's useful. So we have the physical representations of the surfaces that line up kind of very well, or should line up very well, with our volumetric data if we project them into the volumetric space. Those are great. But we also have these other ones where we've changed the geometry, not the topology, and then these have various convenient features for visualization, for alignment, and things like that. And that's what the specification file kind of notes automatically for us. Okay, now, why is this particularly useful even beyond visualization? Well, let's think about if we were analyzing data on a volume. So consider here this AFNI view. So this is a surface, and I have 2 points A and B that have a short straight line distance between them. If I knew nothing about surfaces or anything like that, you just gave me these coordinates, they're maybe a couple millimeters apart, let's say. Now, let's think about the way the brain is organized, and let's think about smoothing. When we acquire our data, it's smoothed. So the information that we get from the MRI scanner is spread around a little bit, doesn't kind of come point-wise. But also we typically blur our data. And so if I blur my data with a few millimeter radius on the volume here, the information from these points would be blurred together. Now you might say, well, blurring is okay. I want to blur gray matter with gray matter, and these are both gray matter, so that's okay. It should enhance my signal. But let's think about that. First of all, there is some white matter here that's being blurred in, so that's not great. But second of all, the way the brain is organized, this part of the brain and this part of the brain might do something totally different, right? This might control motor, and this might be auditory. Okay, that I know those aren't actually the cases, but just something, two different parts of the brain, because they're very far apart on the topology of the surface here. So if I'm constrained to go on the surface, then I see parts that are local on the surface maybe work together here, but just because they're close, not constrained to the surface, doesn't mean that they actually work together. So this is the same thing we talk about distance as a crow flies. It's very easy for something that can elevate above the surface of the streets to go between 2 points, but if you're constrained by highways and roads and obeying traffic laws, then your route may be much further to get between 2 places. And again, this really matters in particular for blurring our data together. If we want to blur our data, we'd like to not just blur only gray matter together and avoid white matter, but we also want to avoid like gray matter or appropriate gray matter with it. So geometry proximity does not imply topological proximity. Just because these 2 points are close geometrically doesn't mean that in the geometry that matters, or in the topology that matters, here constrained to the surface, they're actually close and related. In fact, they're not. And so this is why we might want to project our data onto the surface, then do blurring, because now we're only going to blur with gray matter, and more particularly with the gray matter that's right here. Because sometimes you'll even find, the sulcal and gyral patterns will be such that it's really gray matter, but now you're really in a totally different part of the brain. Again, because it's not, if you don't take into account the surface that's actually here. Okay, so hopefully that makes sense. And again, this is why you might want to project your data onto the surface before you do blurring. And this is something we'll take a look at with AFNI Proc, because you can process your data and project it onto the volume, project it from the volume onto the surface before blurring, for especially this reason. Okay, these are the families of surfaces that come from FreeSurfer and then AT-SUMA MakeSpec, and they're these kind of anatomically correct ones, let's say. So the geometry is such, if I take these and project them onto AFNI, which we did earlier on, then I see that they should, assuming everything went well with the recon all, they should fall into the kind of correct spot, and I can check that. These other ones are not the same geometry, so if I projected this here, it wouldn't really make sense. But the nice thing is these all have the same number of nodes, and node number 5 here is the same as node 5 here, and here, and here, and here, etc. here. And so however I project my data, or however I view it, I can always kind of correspond to the node. So even if I look at my data here, I know that node number 5 in one of these anatomically correct ones should, let's say, go here, and it can always find its way back. So just because I view a surface inflated or as a sphere or flattened out, that doesn't mean that I can't find the appropriate spot in AFNI. Okay, so this is what we mean by kind of nodal correspondence. And this is all just kind of within one subject, but in AFNI and SUMA, we use standard meshes. So ideally, by the time we have our data, again, if the programs have worked correctly with the alignment and things like that, actually node 5 in every person's surface should correspond to the equivalent spot here anatomically. Okay, we already looked at this a little bit. You can view multiple surfaces, and you can go through this. So the period and the comma key move you through this this set of surfaces that have been created, and space key will go back and forth between the reference state, the kind of home state, and your current one, and control N opens up a new controller. So we looked at that a little bit before. You can control how the surfaces are locked. So by default, if I rotate one, when I have multiple open, they all rotate, things like that. And you can choose how to do that. Okay, so let's talk about the idea of standard surfaces, standard meshes, because just like when we do volumetric analysis, we want to be able to combine lots of people's data. So in a volume, I have a voxel as my unit that carries information. And when I warp something to standard space, what I'm saying is in every subject's data set, the voxel at some ijk location should correspond to the same place that was in the original subject's brain, right? So I push and pull those around, but the information that was in my original subject is now here, and I can stack all those voxels up on top of each other and average them or do a t-test or whatever, right? So that's what we do. We warp the brain so that information from an individual subject's brain at gyrus X goes to gyrus X in the template, and hopefully every subject's brain does fine. Once we've checked our surfaces for quality, we saw how to do that by having AFNI and SUMA talk to each other. Then the nice thing is that we're done with our standard space mesh normalization. There is no extra step. In the volume, we have to push and pull the brain around. In the surface, when we created the surfaces, we actually lined them all up and we gave them a standard mesh. So these meshes that you see here are standardized. They all have the exact same number of nodes. So this standard, let's see here, let's say this one, this smooth white matter and this peel mesh, this Gifty file in this subject, whose label is FT, will have the same number of nodes as every other subject that I put through recon all and used and brought through at SUMA makespec FS. Okay, so just to note, the surfaces when they come out of FreeSurfer are not standardized. When you run at SUMA makespec FS and bring them into AFNI and SUMA as a convenience, and we standardize them, and we make two densities of them, 141 and 60. So I type 3D info on the Gifty, oops. If I type 3D info on this data set here, I can see that this standard 60 data set has this many, they're not actually voxels, but they're nodes. and the 141, which is also here, has a lot more, almost 200,000. Okay, so the difference between the standard 60 and 141 is simply the number of, again, not actually voxels, but nodes. And if you want to learn more about the standard surfaces that SUMA creates and kind of started for the field, I think other software has started to do this now. You can read about it in this paper that talks about the alignment and the standardization process. Okay, so again, for group analysis, what we just, this is just defining what we usually want. We want the same thing that we have in the volume. So we want every node, so node 578 in every subject's brain to correspond to this part of this equivalent feature in their brain, right? That anatomical feature. So that's what we're hoping for when we do alignment. And so the way that it goes, or the way you can think about it, is you take a subject's brain and let's just kind of paint one sulcal feature here. And if you inflate it, you can see that's what it looks like. Fine. And now what we want to do is, for our reference template brain where that same feature exists, we want to basically have the corresponding part. So once I inflate my mesh like this to the sphere, I can think about wanting to take all these nodes and rearrange them and have it end up looking like this. Okay, so we do this by, if you think about this as kind of a mesh, like a chicken mesh or something like that, you can take nodes and push and pull them around, but you can't break it. So we want to preserve the topology. So we push and pull the nodes around, but we don't break the edges. And another feature that we want to have with this is anytime we do alignment and things like that in the volume, if you follow those volumes, we talk about anytime you regrid your data, you introduce smoothing and things like that. And what we want to do is we want to preserve as many good properties as possible. So what we want to do is we want to basically end up with a similar mesh. So however many nodes and things you have here, we want to have the same number of nodes in the output, and we want to have a similar topology. We want to be topologically isomorphic. Okay, so in order to do that and to still not blur the data or smooth as much as possible, the way that SUMA does it is you interpolate using the coordinates of the original surface. So we want to preserve geometry and have this kind of nice mesh around here as well. We don't want to have topological defects, and we don't want to blur the data as we interpolate it. Again, if you want to read more about this, you can look at the original SUMA paper or the one that I just showed. Okay, and now at the end, first of all, we want to see that as we standardize our mesh, so we don't really lose a lot of geometric properties as well. We don't want to cut off features from the brain. And anyways, especially the higher resolution meshes, the anatomical before and after this standardization process are almost indistinguishable. So for the geometry is preserved through this process of standardizing as well. So for every subject who comes through Recon All, you get a mesh. You're not guaranteed the same number of nodes. So node 58 in this subject and node 58 in another subject may be in totally different parts of the brain. After you've run @SUMA make spec FS, node 58 in this subject and every other subject should be corresponding. It should be all in the same anatomical feature of the brain, as much as brains have that kind of correspondence. And in this process, you shouldn't be losing a lot of the geometry of it as well. It should still fit back over the brain well. Okay, so here are 6 different subjects' brains, and we're showing them all basically their mesh for their individual quirky brain shape, right? If you look at these, you can kind of see that they have different sizes, a little different shapes and things like that. However, in a volume, if they were standardized, we'd expect them all to look the exact same. They should look the same size. They should all look like the M&I brane that they've been warped to or something. Again, in SUMA and on surface meshes, we don't have to worry about the geometry looking the same. What we need to have is that all of these 6 different branes have the same number of nodes, right? That's node correspondence. And then each node of the same index, so let's say this is node 57, then node 57, I'm guessing in this mesh is here, and in this mesh it's here, and this mesh it's just over here, and here, etc. Okay, so these have been colorized by their node index value. So let's say here, node 120,000 is this kind of orange, so maybe it's somewhere around here, something like that. Okay, and this is quite useful because this means that you can take anybody's mesh and look at it on any brane. You can show their standardized data on their own quirky brane, or you can take those 200,000 values and show them on a standardized surface that has the same 200,000 values, where node 57 corresponds to the same location in that standard space. So you can present the data in a way that's most appropriate. Okay, and again, this is a feature of having at SUMA MakeSpec FS having standardized the meshes that come out of FreeSurfer. Here's an example of what the same kind of coloring node, the coloring is by node number. These are what the original meshes look like. These are not standardized. The bigger brane here has more red. It has just more points in it. The node, this might have 250,000 nodes. This one might have only 175,000. This might have 185,000, etc. And then if they have different numbers of nodes, fairly obviously a node here doesn't have any correspondence around here if I just try to take its node index. Okay, so hopefully this idea of what a standard mesh versus a non-standard mesh is makes a bit of sense. These are meshes that are not standardized, and so I can't just pick the same node number and show the crosshairs there and expect it to appear in the same anatomical feature. These have been. And so once I pick a feature here, the crosshair on the equivalent node should appear in the same anatomical location here. Okay, the way these are created, again, with FreeSurfer output, is this at SUMA MakeSpec FS. And if you want to, you can read about it with this map icosahedron, which is a program in AFNI, and it makes these standard surfaces of 2 different densities, the standard 141 and 60, and what those correspond to. Here you can see the number of vertices in the 141. We saw this just a moment ago. This basically corresponds to being spread out over kind of a 1 millimeter distance scale, and this corresponds basically to the somewhat analogous spatial resolution of your originally acquired data. That's why this number is chosen, why it exists. The standard 60 corresponds roughly to kind of standard EPI data that you would acquire. So again, having the nodes spaced out over a somewhat similar distance that your actual data was acquired on. That's why they were chosen. Okay, let's see, let's pause here. There are programs for comparing surfaces, and well, okay, let's just do a little more. We can compare surfaces and perform surface metrics. We'll look at those in another program, but you can find distances, areas, and things like that on the surface, and all those can be useful. There are programs to help try to deal with topological defects that may come from the surface estimators. A topological defect would be something like this, where your mesh gets wrapped up on itself, or you don't have like a smooth surface anymore from it. So anyways, all these things can be checked for, and then this is a useful feature. The SUMA data should be aligned to the experiment when it comes out. You can also align other data. If you end up moving your anatomical or rotating, let's say, you can rotate your surfaces and things like that, and align them so that you keep all your data together. Okay, So let's pause there for now.